Video we'll go through perpetuities and what perpetuities are and how we can make calculations relating to them. So a perpetuity is a situation where somebody invests money. Okay, so it's an example of an investment where we put money into the bank account. And like with any other investment, once it's in the bank, that account balance will generate interest. So interest gets added on to the balance. And the investor withdraws money at regular time periods. Okay, so they take money out of their account over time. But every time they take out money, the amount that they withdraw is equal to the amount of interest generated. So essentially, they're just taking out the interest that's earned on their balance. And so because of this, the overall balance of the account always stays the same because we're just taking out the interest, but the actual amount that we invested at the start just stays the same. And so on a graph, over time, a perpetuity just looks like this, where the balance isn't going up or down because really what's happening in between each time period is we're just getting a little bit of interest, but then we're taking that interest straight back out. And so over time, the balance doesn't increase or decrease, just stays the same. You don't have to know this, but the term perpetuity actually comes from the word perpetual, and perpetual just means never ending or never changing. And so these scenarios can actually be modeled in a very similar way to interest-only loans, because you might remember from 9D that interest-only loans were where we borrow money and then only pay back the interest. Okay, so again, even though it's a different scenario, the numbers are behaving the same way. All right, so for perpetuities, we have this formula that we can use to calculate the payment that will be taken out from the perpetuity each time period, and that formula is P equals V0 times R over 100, where P is the amount of money that we're actually going to get paid, so that's our payment amount each time period. V0, as always, is the initial amount invested, and R is the interest rate per compounding period. Okay, so again, if R is, if the rate's compounding monthly, we'll have to divide by 12, or quarterly, divide by 4, and so on. The other thing that's worth noting is, just like with any other formula, sometimes you might have to kind of use it backwards to figure out a missing number. So you might get a question where you actually know the value of the payment, but you have to find V0, or you have to solve for R or something like that. So we can use this formula to work out any of those three values depending on the information that we're given. Okay, so let's have a look at an example. This time we've got Jose investing in a perpetuity which pays 5.3% per annum compounding quarterly. And the first part of the question says, if Jose invests $100,000, what will be the quarterly payment from the perpetuity? So what we can do here is actually just use the formula that we've got, remembering that we have to adjust the value of R. So the annual interest rate is 5.3%, but the quarterly interest rate is 5.3 divided by 4, and that equals 1.325%. So I know it's already on the screen there, but we could use our CAS to check that and make sure we've got the right percentage there. Yep. And so then we go to the formula and say, well, the payment will equal V0 times R over 100. So that's just using the formula that was on the previous slide there. So payment equals V0 times R over 100, which in this case is $100,000 because the initial investment is $100,000 times 1.325 over 100 and, whoops, how many zeros is that? 100, two more, times 1.325 over 100. Chuck that into the calculator. That tells us that we're going to receive a payment of $1,325 each quarter from this perpetuity. Okay, so really what's going to happen every quarter is that's how much interest his balance would have generated, and he's just going to take that money out and do what he wants with it. Okay, second part of the question says, if Jose wanted to receive a payment of $600 per quarter, so maybe he's decided that he doesn't actually need this much money, he only wants $600 per quarter, how much would he have needed to invest in the perpetuity? So this one's saying we don't know V0, okay, but we're going to try to work it out. So it's one where we're going to have to use the formula backwards. So the payment, or when we look at our formula here, the payment is $600. V0 is the thing we don't know, but R, the interest rate, is still going to be the same as what it was originally, which was 1.325% per quarter. So those are the numbers that we can substitute into the formula, okay? But when we do that on the CAS, if the unknown number is on the right-hand side of the equation there, then we can use solve. So we're going to say solve 600 equals Instead of V0, let's use X because that's the easier unknown number to enter, times 1.325 over 100. Remember, calculator always solves for X by default, so we can just hit execute, and we would get that he will need to invest, or V0 would equal $45,283, and so that would be the required investment if he only wanted to receive a payment of $600 per quarter. So as you can see, with this formula, you sometimes have to work backwards to find V0 or find R, and if we do have to do that, then using solve on the calculator is the best bet. Second example for perpetuities, we've got a multiple choice question, and it says, which of the following recurrence relations could model a perpetuity? So we've got three different options of recurrence relations, and our job is to find the one that would model a perpetuity. So remember that what a perpetuity does is it's a bank balance where the value of the investment stays the same. Over time, it doesn't increase, it doesn't decrease, it just stays the same. So what we're trying to find is the recurrence relation where the initial value will be the same as the value after one time period, and then the same as the value after 2 and 3 and 4. In other words, if we start calculating B1, B2, B3, B4, and so on, we keep getting the same number over and over again. So let's look at each of them carefully. Option A says B0, well, they actually all say that the initial value is $75,000. But in option A, the recurrence relation has 1.005 times BN, so this would be like adding a bit of interest, plus 550. So really, without even checking it on the calculator, we can tell that those numbers are going to be increasing because that interest is going to add some value, and then adding 550, well, that's just going to make the values go up and up and up. And we can double check that, right? We can say, well, 1.005 times the initial value, which is 75,000, plus 550, well, that goes to 75,925. And then if we took that answer and multiplied again by 1.005 and added another 550, well, the value is just going up and so on and so on. So that one's definitely not a perpetuity, right? Because in a perpetuity, the value shouldn't be going up or down. So we can rule out option A. Option B looks a little more promising because it's got a 1.005, a sort of multiplier that would give a bit of extra interest. And then this minus 650 indicates that that would be like money coming out of the account. What we have to check is whether the values are actually staying the same. So similar idea as before, let's put the recurrence relation into our calculator. 1.005 times the initial amount, 75,000, minus 650. Okay, and notice that the value's actually gone down. So this would be the value of B1, but it's $74,725. And if we did repeat the calculation to get B2 or B3 and so on, so multiplying the previous answer by 1.005 and subtracting 650, well, again, you can see the values continue to go down. So that one's not a perpetuity either because the values are supposed to stay the same for a perpetuity. So we can rule out option B, which means we kind of know the answer is going to be C, but we can double check it by making sure that if we actually work out the first few terms of this recurrence relation, they should give us the same number over and over again. So let's try it. 1.005 times 75,000 minus 375, and if we hit execute on that, we get $75,000 again. So that must be the recurrence relation where the interest that's being added on is exactly equal to the payment that's being taken out. And so the two things cancel each other out and we just get a value of $75,000 in the account again. And if we did it over and over, we would just keep getting $75,000. So B1, B2, B3, B4, and so on, all equal $75,000, which means option C is the one that models a perpetuity.